Ladies and gentlemen, distinguished guests from as far afield as Australia or just next door in France from the French Embassy, welcome to the 41st Maurice Lubbock Memorial Lecture on the rise of the machines. Delighted to be able to welcome you to this, which is the most prestigious lecture that the Department of Engineering Science has. We've had many prestigious lecturers to go with the lecture every year, and we have somebody who I'm sure you'll really enjoy listening to in a few minutes' time. Very briefly, just to tell you that the lecture is in memory of Maurice Lubbock. Maurice Lubbock was a British industrialist. He was on the board of Lloyds Bank and Rolls-Royce, and he was the chairman of production engineering in the 1930s. I really believe that British engineering had a major contribution to make the life of the country, both in terms of improving the quality of life of people and also in the creation of wealth. And so in that particular context, we couldn't have a better lecturer than Professor Hugh Durrant-Whyte. Hugh arrived in Oxford 30 years ago now, straight from is it UPenn or UPenn? University of Pennsylvania. Did a one-year postdoc and then was appointed as university lecturer in the Department of Engineering Science. And in fact, we got to know each other because I think I was the next but one appointment, and I had the office next door to Hugh for just under 10 years. It was a great blow to the department, I think, when he went off to Australia in 1995 to take up the chair of mechatronics at the University of Sydney, from which he very quickly established a network within Australia. He set up the Australian Centre for Field Robotics, which I think is known worldwide for real-world application of robotics, especially in the mining industry, funded by companies such as RTZ. And he ran that very successfully and made it grow to one of the leading such institutes, not just in Australia, but in the world, before he accepted the position of chief executive of NICTA. Now, NICTA is a very interesting institute. It's National ICT Institute or National ICT Australia. It was a $100 million per annum institute, 50% funded by government, 50% funded by industry. So Hugh's had a track record of developing real-world applications of robotics and autonomous systems, but at the same time, he's a brilliant and very innovative scientist and engineers, for which he was recognized by the Royal Society in 2010 by being made a fellow for his work on decentralized sensor data fusion and autonomous vehicles. So he has a pedigree of real fundamental science, mathematics, and engineering with applications that have made a difference to hundreds of people, if not thousands of people, throughout the world. So I'm absolutely delighted, after a 20-year absence, Hugh, to call you to give the 41st Maurice Lubbock Memorial Lecture. Thank you very much, Hugh.
It's an enormous pleasure to be here today. Yeah, it's 20 years this month, actually, since I left Oxford, and I see the weather hasn't changed too much. I also say this is a very, very daunting lecture. I have my mentors, I have my ex-colleagues, many of my ex-students here as well. It's the kind of, your entire life flashing before you kind of view from the stage here. So it is a little bit daunting. Nevertheless, I'm going to try and do three things today. I'm going to give you a little bit of what I've been doing in 20 years and say a lot about the progress that robotics has made over that time and the impact that it's having, particularly somewhere like Australia, but I think it will have a lot of impact in UK and Europe and all over the world in the coming decades as well. Secondly, I want to kind of also link that to something that I've been doing really over only just the last 5 years, which is re-looking at things like machine learning and AI and looking at other ways that we can apply it. And I will say, I think what robotics has done is a bit of a favour for AI. It's kept the light of AI burning in the time that, in some sense, no one had any faith in it, and we were using it and applying it in building robots. And so there's a very strong link to all the fanfare you see these days about machine learning, and robotics had a big part to play in that. And I think lastly, I want to just put a little bit of emphasis on the fact that we're heading towards a future that I think is very uncertain. And AI is contributing to that, perhaps not in the way that popular media has it, but we need to be cognizant as engineers, as people in society, what it is we're doing towards the future. So that's kind of the vista of what I want to do. So 20 years ago, I moved to Australia, and the great advantage of Australia, of course, is that it's big and it's empty and it's a long way from anywhere, which if you want to do robotics is kind of perfect because there's lots of things you can automate, there's plenty of spaces that you can go and do this kind of thing. There's also great industries that really have a business case why they should use robotics. So mining we'll come to in a little bit, but that's a very good example of an industry where you could imagine automating would bring lots of benefits, not just productivity and things like that, but safety and ability to do things that you could not do otherwise. And so that's a very compelling case for doing this sort of thing. But equally in Australia, all the sorts of things like remote operations in the middle of nowhere, agriculture, materials handling, all these sorts of large-scale things. And I have to say, you know, there's some enormous research challenges as well as business challenges in making this happen. And Australia's been the perfect place for me to make this happen. Having said that, I actually started this kind of exhibition, this sort of process while I was here in Oxford. And I want to put a little bit of story onto it because there are people here who remember what it was like at the time. I can see Ian smiling there. I was in a bar and a man walked in and he said, well, could you automate a container yard? This guy called David Avery. And I have to say, you know, it was the start of something big for me because I was the normal academic. I did stuff in the lab. We had the basement in the Jenkins building and we built little robots and we watched them running around. But making big robots, really, really big robots, out there in the real world going really fast was kind of exciting, right? It was like Thunderbirds. And so it was really a nice challenge to do this sort of thing. And I will say this was in the day and the age before people really thought about self-driving vehicles at all. So while I was being a happy academic most of the time in the week, the rest of the time in the week I was building big vehicles like this. So this is 1990, okay, so this tells you 25 years ago we were building self-driving vehicles and a lot of the technology developed inside the robotics group at Oxford. This is a machine with 12 transputers on it, so if anyone remembers transputers, okay, this is the kind of thing that we were using at the time. And it had radical different bits of technology. There's a millimeter wave radar you'll see in a second on the side of it, so we were developing new types of sensor technology. We were trying to figure out what happened when you really built big vehicles and drove them at speed and how you control them. So new control algorithms were a big part of it. How did you do planning? This was actually a project that actually Andrew Zisserman and Stephen Cameron were all involved in at the time as well. Really how to make this kind of stuff work. There's the radar. So it was really exciting as far as the technology went, and it was completely useless as far as the business case went. No one was interested. What were these academics doing with things like this? And also we learnt useful lessons. I like this one. There's one of my students from Oriel here. This is what we did with students in those days. It's possibly illegal now. This is a vehicle, the first time going backwards, you can see the R for reverse there. And many people who know me also know that despite doing all these autonomous vehicles, I don't drive. So I actually am not really clear about which way you turn the steering wheel when you go backwards, okay? And so this is the kind of thing that, you know, my wife says, your left, my right. And you'll see Eddie there realizing that I have not actually got the algorithm right. Okay? But that's what we used to do with undergraduate projects in those days. So it was interesting. After doing that, I really was bitten by the bug and realized I could not do large-scale robotics in a place like Oxford. The roads are too small, they wouldn't let me use the parks and things like that. So Australia was the place to go. But intriguingly, the first project I worked on was kind of a repeat of the first project. And the great thing about getting a second chance to do the same thing is you knew all the things that were going to go wrong in advance. So you could kind of apply it to these problems. So I have to say I was very fortunate in meeting someone immediately I got off the plane that said, could you automate a terminal? And I said, yes, we could do that. And I think the nice thing here also was all the research that actually we'd done at Oxford at that time. And I go back to people like Simon Julia, who's now a reader at University College London, who was building large vehicle models, trying to figure out how we could operate and control vehicles. People who were trying to understand how you build very high integrity navigation systems that guaranteed never to go wrong. All right, this is a very hard thing. If you're driving a big vehicle, you clearly have to make some guarantees about no failures, all right, in some sense. So there was some very interesting and sophisticated mathematics that went into that. Equally developing radars, and again, this is an interesting area because a very successful company, Navtec Radar, got founded out of it, which is now based in Didcot and makes a lot of really interesting products out of it. And also worrying about safety. You know, so, I guess after the video I've just shown you, you kind of get the idea, right? How we were going to manage safety in some kind of way. So this was a great project also from the point of view of learning about business. And I think this is something what I've really enjoyed in the last couple of days is seeing how the department is really so much more externally focused now with lists of the startup companies on your webpage. And I think this whole understanding how what we do interacts with business is so crucial to the future of where we are. So in several different things for me, how you actually change the whole way you do business. You know, it's no longer about moving a box, it's about the whole supply chain. It's, you know, integrating everything together. And we'll come back to this a bit later when we talk about mining. It's how you get commercialization models together that benefit academics, that benefit industry, that really allow you to make these things happen. Labour reform, we had some real issues in Australia and there was a big national strike over this project and things like that. And we learned a lot of things about how to do things perhaps more delicately in the future. And learning about business plans, you know, we always talk about it. You know, a business plan is a work of fiction until someone really has a customer, okay? And here was a real thing. Do you just build automation? Do you build straddles? Do you actually offer to run someone's terminal at half the price? You know, what's the business model that really makes you happen? So these were all enjoyable things that we did. And equally, we also learned the obvious lesson that it takes time to get these things right. 10 years is the minimum to really make a project succeed. And I think just even talking to someone a little bit earlier where they were doing something not dissimilar, it takes that length of time to go from these sorts of concepts to something that in the end is a product that actually people can use. And most importantly, the success of a project is when you walk away. If you can walk away, that's success. So we started all the way out with basic platforms. You'll see actually the little trenches that we've dug in the ground there because the ground wasn't solid, all the kinds of things that you don't think about, up to the first prototype vehicles where we had 4 of them running around a new terminal, to operational testing where we started unloading ships and these sorts of things, all the way to the time where there was a complete production system and you actually walk away. This is a real learning experience for me in so many different ways. And this is the project in the end, it'll always be, I suspect, the one that I'm most proud of, because I have nothing to do with it anymore. All right, it actually works. So this is it in action. This is the Brisbane terminal circa 2007, 25 straddle carriers. It is a sight to see. It's a sight to see because no one at this terminal even looks at the things, all right? Because they just assume everything will work. And I think the other part of it that's very important is it is a whole system, everything from ship all the way to the rail and the train, and the robotics just make it sort of come together as a different part of the business process. They've just opened up Port Botany, which is another 45 automated straddle carriers, and they're about to also automate Melbourne. So this is the kind of technology, suddenly things are actually sort of accelerating and going away. And much of this, I'll come back to, is key technology that was actually originally developed in the robotics group here now 20 years ago. However, I will say I went to Australia for a good reason. Big places, big holes in the ground, things like this. This is Mount Tom Price in the northwest of Australia, about 4,000 kilometres from Sydney University. So this is our second lab. This is an iron ore mine. And basically there is a piece of iron in Australia that's about the size of France. Okay, it's 65% pure iron, and they spend their time digging it up and exporting it. Okay. And this is an obviously huge, wonderful robotics challenge because not only do you have automated vehicles, you have planning, it's outdoors, it's dusty, it's big, you know, and it's billions and billions and billions of dollars. These are enormous investments, okay? And so being able to come in here and try and automate it is really the reason I went there in the first place. It was such a great thing. And also, despite the fact there's a hole in the ground, it's great traveling around Australia to all these remote places and seeing what goes on. So early up in the piece, we kind of said, okay, we're going to do the basic stuff. So this is back in the early second half of the 90s. We're going to try and automate vehicles. So there's this one over here, for example. This is at Mount Isa. This is an underground load haul dump truck. And we're going to fit it with sensors. And there are people like Mike Stevens, if anyone remembers Mike Stevens, who ran this project, who again came from Oxford. And we designed SLAM automation systems that would guide these vehicles up and down tracks in underground mines. Here's another one over here. This is a great one. This truck actually doesn't have anyone in it, all right? And this is a test of the collision detection system. This is the guy who paid for it. So, you know, I guess if he gets killed, then he wouldn't pay us. And this really, again, tried to bring together some of the sensing, the detection technology, all these sorts of things to bear to really show we could do stuff. But I will say at that point, mining was not ready for automation. It was an interesting process. They were interested in us providing components that would make trucks work better, be safer, or image, or do something like that. But no one really had the concept of how you could build this completely huge automated mine and operate it remotely, perhaps even from a different country, which is the kind of vision that you want for something like this. So all of that happened, and then I want to come back a little bit to where I was, at the point where we left the cargo handling stuff. The breakthrough came when I took some mining executives to that automated terminal, and they took one look at it and realized what was happening. They realized actually it wasn't really just about the robot, the straddle carrier, it was about building a totally different business model, all right, where everything in the whole process was automated to some degree, where you really had control over what's happening. And probably the most useful slide I ever put up in front of an executive was this. I reckon I've made nearly $100 million out of this one slide. And what it shows, all right, is that it is not about building an automated truck or anything like that. It is about the control of information. And automation turns out really to be about information control, about how you use information, whole things like that. And just to talk you through briefly what happens in mining, typically about 5 years out, you drill a few holes and find out what's underneath, all right? Then you do nothing. All right, until about 13 weeks before you dig it up. And at that point, okay, you then start drilling it to put explosives in it to blow it up so you can dig it out, all right? And typically what happens is, having done that, you then blow it up and you don't know anything about what you've done. So automation, all right, is really about let's do something different. Let's control the information, reduce the uncertainty that we have in the mining process by automating surveying, by automating drilling, by automating the whole process so that it is controlled in a way that it actually allows you to predict ultimately the product that you're going to deliver to the customer. All right? So you can imagine a big supply chain with different bits of information and different bits of automation throughout the whole thing. And Rio Tinto bought this. Okay, and we'll come to it in a bit, but they've expended nearly $6 billion on this concept in the last decade, all right? That is, they take the entire mining cycle and really automate it. And automate it in a number of ways. So design the architecture, do the data fusion, which is where you have to put all this information together to really come up with one picture for what's going on. And actually the last thing of interest in the end is actually the bit where you build big automated trucks. Although we do have them, and I'll show you them in a minute, in the end they don't actually contribute as much, nearly as much, as actually managing that information flow and how it actually sits all together. So Rio Tinto now have this thing out there in about 19 different mines. This is called the Mine Automation System. It's an open architecture. In fact, we persuaded them very early on to open source this. So they're the drivers, they produced it, but now in effect every mining company has to use it as well. And that was a really good business decision at the time. There are things you need to make open and things you need to keep close, and this is the sort of thing you want open. So as we'll come to in a bit, you can actually now sit in a room in a place in Australia and control mines in the Pilbara, in the Hunter Valley, in Mongolia, in Utah, all over the planet from one place. All right, it's a magnificent thing to see when you stitch it all together. The second really critical thing was actually putting together all the information in real time for what was going on in the mine and building one picture, which is what drives the automation, which drives the whole business. So there turns out to be lots and lots of different types of information in a mine, where the trucks are, what the surface looks like, what hyperspectral images of the face look like, what laser scans look like, what drilling information looks like, and what you want to do is to integrate that all together so you end up with one common picture of the surface, of the subsurface, and all the chemistry. All right? And imagine that being updated in real time by all this equipment that's going around, whatever it may be. And this actually turns out to be the key to successful, efficient mining, is building one integrated information picture for what's going on. And finally, automating equipment. Now, I know this looks cool, but actually I want to emphasize this is almost the least important bit of it. All right? So I'll show you in a minute automated trucks. We now have automated trains. They've just been running since the beginning of the year. And these are non-trivial things. They're 6 kilometers long. All right? So huge automated things. These trucks, incidentally, when fully loaded, are 600 tons. So bigger than an A380. Okay? Automated drills, automated shovels. It really is like Thunderbirds. It's such good fun. So here's the trucks. It actually has very much the same technology on it that you see on the Strad with radars. So these are all the big unmanned trucks. There are now 150 of these running in the Rio Tinto Pilbara operations. Each truck, as you can imagine, is a big item, fairly expensive. These shovels are not yet automated, but it kind of gives you the idea. And it's, again, radar, it's GPS, it's all this guidance technology. Again, the sorts of things that were developed here back in the early 90s and so on. So it's an interesting program. It's great to watch them. These are the self-driving vehicles that actually make money at the moment. Okay. Second thing I want to show you is the drilling program. Hang on, I think, yep, this is it. Now this actually turns out to be more important than the trucks. And the reason is, this is the first time you get more information than you had when you were doing exploration. So as you're drilling, so what happens here, and some of you I know won't be familiar with this, but in order to do mining, you drill lots and lots of holes, all right, where you want to do the mining, and then you fill them full of explosives and you blow it up, okay? And then when it's blown up into the right kind of pieces, you then excavate it, and that's what you actually do. So the drill, as it's drilling, has pull-down pressure, rotation pressure, it's got chemical sensors. We actually have an X-ray machine on these platforms as well, so we can determine the chemistry every time we do the drilling. And then remotely, you can see the geologist actually sits 2,000 kilometers away, all right, from this mine, and he can actually pull up a picture of what he expected the mine to look like, what the drill says it is, and then generate from that an integrated picture of what it is they're about to mine as it sits in the mine. Okay, so this really is a whole data fusion process. Lots of interesting types of sensors, trying to build in real time a model for what's actually out there. And that's really the advantage of automation, is to give you this knowledge, to give you this precision that actually allows you to do what you actually wanted to do in the first place. And that really is the payoff, the economic payoff in these sorts of things. Now I wanted to just see whether I could, might not, yes it might happen. I wanted to go a little bit more towards the end. Yeah, it gives you, so you can see that's what happens. It's really good setting off these explosions too, okay? So just to put a little bit of technology in here. So again, this is sort of things that we've been trying to do quite a bit of. These are quite different data fusion problems because you want to build a model, if you like, that has spatial continuity, that has information that basically says, well, if you expect a piece of ore like this here, then you'd expect an equivalent piece nearby. So we use these Gaussian process technologies, which are, again, being pioneered in machine learning over the last decade at least, but also some non-stationary characteristics. So the fact that one of the important things in any kind of mineral exploration is the fact that rocks have edges, all right? You want to be able to distinguish where the boundaries are in these things. And to come up in real time with information that takes the a priori model of what's down there, the information from drilling, and comes back in real time with a picture of what's going on in terms of the iron ore concentration, but also the chemistry of the different types of contaminants that are involved. So this operates in real time as the drill operates itself. And then finally, remote operations. This again has been pivotal. We started by building a little kind of shed, okay, where we did this. We then moved it to the university, and there was a point where we were running a mine from the University of Sydney. We just didn't tell the university what we were doing. And eventually they built what I think is incredibly unique, which is this remote operations centre near Perth Airport, in fact, which operates all 13 mines in the Pilbara from one office. Okay, and that is everything. It's not just the equipment, it's the geologists, it's the trains, it's the whole loadout procedure and so on. And I think this is really innovative because it shows you, in some sense, that original concept that says you can do complete remote operated, automated mines at this kind of scale. Still a long way to go. As I said, Rio Tinto have invested close to $6 billion in this program. This is arguably the largest civilian robotics program ever undertaken anywhere in the world to date. There are other great problems in Australia around this, and I really just want to mention a few of them. The other big one that we've always been interested in trying to tackle in Australia is around agriculture. You know, we have farms in Australia that are 1 million acres, and you know, people don't really want to live in the bush and things like this. So there are lots of opportunities for trying to automate the whole agricultural process. And again, if you think about it, agriculture is a problem about information again. It's about crop yields, it's about soil qualities, it's about predicting rainfall, a whole range of different things. And in some sense, if you manage that, you wouldn't need to automate it all. But what automation buys you is a degree of predictability and an ability to gather data, to control data, to do these sorts of things. And that's what robotics is buying you in so many different ways. So this is work primarily of my colleague Salah Sakaria, who now runs the ACFR, and it's kind of stuff that's been growing over the last, I would say, 5 years. So it's a lot more recent thing. And economically, I think that's significant. You know, instead of a big mining company, you've got lots and lots of farmers. So how can you explain to farmers what it is they should be doing? And some of it is actually to, in effect, the business model is to hire these things out, all right? So if you want to do crop maintenance or things like that, have a body that can actually do it. So we started out with some interesting work which basically used little UAVs, and this is actually a number of years ago now. Drones are of course much more popular, applying some basic machine learning algorithms to take the camera information that comes from this and actually try and identify and distinguish weeds from natural vegetation. So things like prickly pear, there's a crocodile weed that exists in ponds and things like that, and then identify those specifically and then try and spray them one by one. All right, rather than applying it over a big area. And there have been a number of series of projects in this area. Actually, now we actually run it from a fixed-wing UAV rather than a rotary UAV. But this is the kind of technology that really makes a difference to farmers. And now that this drone technology is out there and is relatively cheap, a lot of farmers are picking up this technology and applying it to their own kind of resources. So another interesting one is this. So this sort of uses the same technology. This is known as the Ladybird. It's an interesting vehicle. It actually is mainly for the horticulture industry, and it really does crop maintenance. A big issue in crop maintenance, and a big issue particularly in Australia, is you can't till the soil. It's very poor quality, all right? So instead of that, you actually have to do very specific weeding, and it's a dreadful job for someone to actually do this. So this is a vehicle that basically comes along. It's got a number of interesting cameras underneath there that can identify different types of weed and distinguish them from the crop. And then actually it's got a series of mechanical arms under there that come along and spray them one by one, okay? Spray them either with insecticide or in fact just with hot water. That's enough, all right? So now you can kind of do organic farming, all right, with hot water, spraying out the different weeds and different sorts of things. So again, this type of technology is actually being used not directly by farmers, but by their agencies, Horticulture Australia and so on, and actually trying to get better yields and better crop management with less use of things like pesticides. So agriculture is another great area for this kind of problem. And finally, I just wanted to say all the other applications in robotics in Australia, I'll just have a drink of water at this point, that have been made possible by the kinds of technologies that have been developed in mining. I'll just mention this one down here first. This is a startup company. It made about 100 million last year, in fact, and it builds sniper target robots. These are robots that run around a target range and people shoot them, okay? And it may look trivial, but it actually involves things like SLAM and a lot of other technology, navigation technology, multiple vehicle control technology, in a kind of niche application where Australia is not normally very good at selling military hardware to the US and places like that. There's a project over here, again, which is always very popular with the students. I know there's one person in the audience who worked on this project, in fact. Basically, again, doing navigation control technologies for underwater vehicles. And Australia has a great coastline and has to manage this in many different ways. This is a project that we did here with BAE Systems, flying multiple UAVs. Again, Australia is big enough, we owned our own flight test facility. It's the kind of thing that you actually need to make that happen. And even slightly more different down here, working with media artists to basically build robotics that engage people in different kinds of ways. So all of this is kind of common technology, navigation, control, machine learning, AI, that I think robotics, not just our group, nurtured over a period of about 20 years, all right, in bringing these kinds of things together. So when I left the ACFR, I wanted to basically kind of take this technology and use it, but not use it in robotics, use it in a different domain. And I think, you know, we've learned so much about how to build robust systems, how to work in real environments and these sorts of things. There were enormous opportunities. So I moved to NICTA and I made a couple of vows. One, I would give up robotics, okay? I've done robotics, time to move on. But secondly was actually to try and do something which would create wealth in an interesting kind of way with data. And I started by basically picking up, I think you've seen it in what I've been saying, a lot of information for us, or the interesting information was spatial. All right? So if you think about mining, you think about agriculture, and you think about Australia in general, a lot of information is spatial. And can you actually use that information in a useful way, in an economic sense, to actually predict the kinds of things that you might want to do in growing new crops, in doing new mineralogy, in actually controlling the environment and things like that. So I built up an interesting group, and there are a couple of interesting projects I wanted to briefly say something about, give you an idea of the scale. So one of the very first projects I started at NICTA was to actually take the kind of ideas that we were doing in mining, but instead of applying it just to a single mine, try and develop it for the entire continent, all right? So you ought to be able to take those ideas, gather all the mineralogy data, all the geological information that exists about Australia, and again, this is one area where data is actually in the public domain, so it's a very easy problem to resolve in that sense, and build up a model of what exists in Australia. And a particular problem we chose was actually in the geothermal energy industry. It's a very interesting area because Australia overlies a big granite outcrop, okay? That's what underpins the continent, and that is typically at temperatures of around 270 degrees centigrade. It's radioactive, basically, and if we just use 1% of that, we could drive the rest of Australia forever, basically. So the issue is, where is the best place to drill? And if you went to a conventional map for what's going on, and this would be typical, what you see is that this is very red, i.e. very hot, and this is blue, and this is very cold. But then when you actually look at the data, what happens is, it turns out a lot of people have drilled holes here, so they know what's going on. So it's red, so they know it's hot. Nobody has drilled a hole over here, and so it's blue, okay? So this is the kind of managing uncertainty bit that I think you need in these sorts of things. And why is it important in the geothermal industry? Well, every hole you drill costs about $20 million, all right? So you want to make sure that the hole you drill is actually going to hit something sensible. And you kind of want to reduce the uncertainty up at the exploration point. And if you can reduce the uncertainty, then you create a whole viable business around geothermal energy. So the challenge is, can you build a model of Australia where all the geothermal resources are, using all the data that exists in one integrated form? And that was really the challenge problem. And we approached it, again, coming from the mining background, in a kind of very different way. And I'll come back to this, rocks have edges. It turns out that when you want to build a model of a continent, the important things are actually not the smoothness bits, they're the edges. That's what you really want to delineate. So a lot of the kind of standard machine learning techniques that assume some kind of regularization don't really operate very well in that domain. So we took a very different approach, which really, I'm beginning to realize, is now fundamentally important to the kind of some of the future of machine learning. So what we did is we have lots and lots of data sources, so everything from seismic to magnetotellurics. Magnetotellurics, incidentally, is the image of the sun as it propagates through the earth, all right? It's a really interesting technology. Gravity, electromagnetics, lots and lots of data sets like that. And instead, what we want to try and do is to fuse all these into a probability distribution, all right, some uncertainty model, over the different types of potential geological model that you might have. So this is not like uncertainty reduction. It's not like the problem where basically you say, you know, where is my curve, and if I add more data, I can reduce uncertainty. This really asks the question, what are the possibilities of all the curves I could have? Do you see what I mean? So quite a fundamentally different sort of thing. And this is the one equation, I apologize to some people here, that I'm going to put up, but it is important. It's probably the one thing you need to know if you ever do machine learning Bayes' theorem. And really what it is in this case is the following. So I'm going to just step down so I can get the pointing right, okay? What we're interested in is geological models, M. Okay, and we might have some prior information on all the possible models because we've asked a lot of geologists what they think is under the ground, and we've taken a bunch of core samples, so we have some indication as to what's out there as well. And indeed, they may say something about its ability to fracture or to propagate electromagnetic energy or different things like that. And then we go over here and we say, okay, what data have we got? D, the data, okay? And we go and ask the geophysicists, look, if you have this thing out there in the real world and you do a seismic survey, what does the data look like? Okay? And if you go out there and you know what's down there and you've got some water in the ground, what does the electromagnetics look like? And so you can start building a picture of what, given a particular model, different types of data might actually look like. And then you can put these two things together and actually create now a probability distribution on all the possible models of geology you could have for the whole of Australia. So this is a very big space, all right? Like a multi-infinite dimensional kind of space, given all the data that I have. So if you can think of this as a big kind of interesting problem. So it turns out this is actually doable to a degree, okay, not completely. So this gives you some idea of what our geologists tell us. We have core samples, and these are very rare because they're core samples at 5 kilometre depth, all right? People don't often drill core samples to that depth. Equally, we have over here, we get geologists in a room and we say, here's some data, use this slider bar and tell me which stratigraphic model you think is most likely given your predilections about the way things are layered and things like that. So we can bring people's own experience into the problem. We then go out there and we do the following thing, and keep with me here. We say, here is a potential model of Australia. if that were the potential model of Australia, what seismic information do you think we'd get from that? And then we compare that seismic information to the information we actually got. And if it's close, then this is a good model, and if it's not close, it's not a good model. And then we repeat it 1 billion times. Okay, do you get the idea? So now basically we have a probability distribution on all the possible models of Australia. All right, I can tell you the geologists get very concerned at this point. And in effect what we end up with is an interesting description of all the geologies, but we also have a probability distribution on all the possible geologies. So this is a very different way of approaching a machine learning problem in the kind of, geology, science kind of area. So the other big thing that we did that was part of this, that we've delivered to open source to the community, is to allow these sorts of very large scale models to run on public cloud. This has really transformed the field in my view. Instead of buying big supercomputers, you can run schemes like this, federate them on, 1 million processors on Amazon Cloud, doesn't really matter, and you can manage different parts of the Monte Carlo process, which is really what's going on here, to generate some of these models. So let me show you some of the things we've been doing. This is the Cooper Basin, that bit where it was very, very red in the picture. So the reason we use the Cooper Basin is there is ground truth. So we can actually test whether our estimates are actually a good model of what's out there in the real world. This is also where most of the geothermal tenements are. And this is geodynamics, what are called Habanero 1 and Habanero 2 sites. And it's really interesting here because we've actually now published a geological paper. It shows you the following. Not only is it hot, can you see this is a probability distribution on granites which are above 275 degrees centigrade at 5 kilometers depth. This is a non-trivial information problem, okay? But more than that, we actually managed to publish a paper because it shows quite conclusively that this was weathered in the ice ages. All right, so 500 million years ago, all right, when the Earth was an ice ball, it turns out that this place here was weathered, all right, by the different ice flows. And that's a really interesting scientific discovery, all right, that comes from using these techniques. And one of the big programs, I don't have time to talk about it, that I'm really into now is actually trying to exploit machine learning technology to actually drive new discoveries in science. And I do think that age is coming where these sorts of things are possible. So this really helped considerably. It probably saved geodynamics $30 or $40 million by actually identifying the right place to put different drill holes. Here is another one that's laden with white elephants, all right? This is actually an inference problem. This says, not only can I tell you what's hot, but because I've got information about how different types of rocks are fracturable, I can actually put a probability distribution that the rock at that depth will fracture. Okay? So this is a model of an area called Pretty Hill, which is in Victoria, which is an area where people are trying to drill for gas. All right? So the elephant in the room here is that, if you like, geology is a kind of a natural resource. You can get heat out of it. You can put gas into it. You can take gas out of it. You can do whole ranges of things. So building models of these big sedimentary basins is really, really interesting. And the ability of it to fracture is important for all of those economic outcomes. So being able to infer those properties at depth has been a real game changer in this sort of technology. So that's one of the things that we've been doing, and I'll just show you a little bit the kinds of extensions that are now happening. In Australia, certainly in New South Wales, we've disallowed coal seam gas at the moment, and shale gas and things like that. And one of the big worries is no one can put their finger up and say, actually, it's safe, or it isn't safe. So you can see where I'm going here. These sort of technologies now allow you to actually put a probability distribution on the kinds of models that will end up being safe and those that are not safe, and actually suggesting to you what kinds of sensing strategy you need to enable people to actually do that. Now, modeling things like aquifers underground is even harder than doing the geothermal one, and the reason is for a number of really interesting areas. Firstly, there's a temporal dimension. So, water flows, and so you've got to model it in 4D rather than 3D. The other thing that I think is really interesting is between samples, interesting things happen. So, the ability of a piece of rock to transmit water, you might take a few samples, but I could draw you one pattern where no water flows and another pattern with the same samples where it does. All right? So these higher dimensional statistics really play a big part. So there's a lot of what we talk of as microgeology and how you embed microgeology into these processes. And as a consequence, we've managed to develop a tool for the government now that basically does the following. It takes all the data that exists in New South Wales about water. It builds up a model, all right, of what that water is. And there is one model that everyone now has to use. Okay, because it incorporates all data. And then people like, in this case, Santos, you can see Santos borehole data coming in, can compare their boreholes to their model. all right? And if they too vary, and you can see in this case they do vary significantly, all right, then basically the model that they're proposing to the government to allow them to do drilling is not valid. Do you see what I mean? So we can actually generate a probability distribution now over the fact that you can, the coal seam gas tenement that you're going to put up is actually going to work in this situation or not work in this situation. So again, it's changing the way governments think about uncertainty. And explaining to government about uncertainty is not a trivial thing. All right? I won't go into that one, but it's a very similar idea where you basically take different types of boreholes and now you have to solve the problem that says, where do I put my next borehole? All right, in order to maximize the information that I have. So here's another application. I have to say we're making a mountain of different companies out of this as well. This is a startup company we generated called InFact Analytics, and it uses a very similar technology but for predicting pollution levels. All right, so you take a number of stations, in this case the Hunter Valley, and you can kind of see sort of the things there, and you can predict spatially between the different things using some of the techniques that I've been showing you, but also we can take this and actually predict forward in time. So predict what pollution levels will be an hour from now, predict what they will be 24 hours from now. And it's a very important kind of thing. This is actually near where there's a lot of coal mining in Australia, and I might propagate it forward a little bit. Just to... Yeah, you can see down here the kind of cyclic nature and the dependency that's been learned that's basically around things like humidity, temperature, wind variability and things like that. It'll all impact on your ability to actually predict wind temperatures. So we've deployed this now in a number of cities as well as in the countryside, and it's hopefully going to be a successful spin-out company. So I want to move on a little bit and talk about some of the challenges as well. Here's a project we've just started actually. Which is not just to build a model of Australia, but to actually build a model of all the potential mineralizations in Australia. This is a geological model of what Australia looks like, and just for your interest, the darker colours are actually old, so that means something like 2 billion years old. The lighter colours are actually quite recent, and you can kind of see how Australia was formed. There is one chunk here that's very old, another chunk that's quite old, and then Australia moved northwards and went over a hotspot and lifted up the east coast. All right? And in the middle, this bit here, nobody knows what's in it at all because it's just covered with like 100 million years of rubbish. Okay, so probably 2 or 3 kilometres of rubbish. And if you look where all the mines are in Australia, the astute reader in the audience will notice, okay, that all the mines are in places where they know what's on the surface. Okay, so the big, what do you call it, $100 trillion question is what is in the middle. Okay, uncover. And the very first thing you should look at is some magnetics, and you can see a lot of the geological structure that exists in Australia, okay, actually propagates underneath that regolith, okay? And I was just talking to someone else earlier yesterday. The challenge here is what are you going to do about it? Are you going to write some algorithms and sell the algorithms and let anyone exploit it? Or are you going to set up a real estate company, all right, that uses the algorithms and pegs its own deposits in these areas? I think this is an interesting question that I'll answer in the next 20 years. So I want to say spatial data has really been the kind of thin end of the data wedge in Australia. You know, the government's gradually changing it, but the great advantage of spatial data is that it isn't allied to people, all right? Which means that it's much easier to put it out in the open domain in lots of different ways. One of the best things that we've done, one of the things that's actually had most impact is something we've made no money out of. This is something called National Map. It's actually been around for about a year now. And it's an interesting idea because all of what it is just a portal. So, it doesn't have any data in it, but it has a front end, and it links to about 20,000 different data sets that government have. And all government have got to do is to put an API in front of their data sets, and then it's available. So you can go to sleep at night, and you wake up in the morning, and there are 200 more sets of data in this system. And the other part of it is that on top of it, third parties, other companies, can actually write their own data analytics and stick it on top. So it's really open source, democratic data in the strictest sense of the word. And I have to say the kind of spin-outs that have happened on the top of this data are really amazing to see. And it collects every type of data. So here you're seeing, I think, tax information and where the aircraft facilities are. So you can figure out whether people who pay more tax have better aircraft facilities or higher real estate prices. I might just go a little bit closer to the end here and also show you some of the more localized stuff. So Down here now, all the state and all the city councils have put all their data on. So this is Ballarat information where all the sports grounds are, linked to where all the water is, linked to how the road quality is. There's enormous opportunities for optimizing infrastructure, for trying to understand socially how all this information comes together. So about 50 different government departments, about 20,000 sources of data. We're actually developing one now for New Zealand, all right? And you can kind of imagine how this thing works. And this is really the great thing about, I think what's been happening is this data being made more democratic and your ability to actually put decent analytics on top of it. Here is one project we've been doing with some of the information, which is, oops, no, I missed that bit out. So let me swap to this actually for a second. So the second bit of my talk is really this, and I noticed this week, the international edition, this is this week's Economist, all right? In the international edition, I think you had David Cameron on the front of yours, all right? But no one else in the world is interested in that. And it's all about AI. And in fact, what I noticed was that the title of their article is Rise of the Machines, believe it or not. So they stole that from me as well. And it's interesting in many different ways because I think AI, I remember a thing outside of Mike Brady's office that had, the history of the perceptron. Do you remember that cartoon? And it started out in 1965 and went around a few loops, came back in the 1970s, went around a few more leaps, came back in the 90s, and I gather it's come back again. It's called deep learning, all right? But I think what's interesting in this area is that robotics has kind of kept the AI flame going in so many ways. And if you like, the good people in machine learning very often did their apprenticeships, in fact, in robotics in different ways. And I've been driving a number of new companies trying to exploit the sorts of ideas that we're talking about here to really try and make the most out of what you can actually do with AI in the modern age. So I want to talk about a couple of these as I go through. So many people now, oh dear. Talk amongst yourselves. There we go. Good. Look, I mean, there are some great applications out there. In lots of different ways. So I've talked a lot about the environment one down here. This is something that I'm particularly fond of for lots of different reasons. There's also enormous opportunities in the health area, and I'll make one little comment about that as I go through, but it's not something I want to focus on. But the two that I actually want to kind of give you some fleeting glance as to where the future is are in the financial and retail area, where I think there are some really deep models now being exploited, and also for me in the infrastructure space. It's the kind of area that people have not really been looking hard enough at, in my view. So we've had a number of interesting startups in this space, and I want to give you a flavor for the kinds of things that are coming in the future. There's a lot of people out there talking about big data and how you deal with that kind of thing, but the real challenge is nothing to do with the data. It's how you kind of get the latent truth that underpins that. So you don't want to know, in some sense, what do people die, what do they eat. What you really want to know is what do they need, what do they want, all right? You want to be able to predict what their behaviors are in different kinds of ways. And we've been doing quite a lot of work in this area in different kinds of ways. One of them, which is again open source, and in fact are being used by people like Barclays as well at the moment, is to kind of extract features from all those sorts of data, to use those features to try and make predictions about different types of people's behavior, and then to use that behavior at a grand scale to say, this is the behavior of all my customer group. This is interesting because this is actually a real set of bank data, and it actually shows you the different kinds of way people behave when they try and repay loans. And the big advantage is you can actually then have a different strategy for different types of people. People who are out of control, people who are basically just scamming the system, people who are basically operating in different ways, and so on. And here's another example I want to bring up, which is sort of the similar. This is actually the Murdoch Press subscription data, okay? And what it shows you is basically how different people subscribe to different information. So a month before they subscribe, a week before they subscribe, the day before, and whether, for example, they read different types of things in different types of orders and this sort of thing. These are all information that's now very commonly available on these sites. But each of those implies some type of behavior. So it turns out, for example, sports fanatics up here will pay almost any amount of money to get a subscription, all right? Whereas people over here don't, all right? And people over here will never get a subscription. And you can actually now start to optimize the amount of resource that you allocate to different types of problems. So you're really going from data to behavior in some kind of interesting way. I'll tell you at this point, I still don't own a mobile phone because I kind of write the algorithms for some of these things. It scares me. Here is actually the mobile phone data. This is Optus data in Australia. And again, there's interesting things. There are the people who never change their mobile subscription, so you can charge whatever you like, they won't change. There are people that swing depending on the different types of phone that you provide them. There are people over here who always go for the cool one, so now you can have a completely different strategy for different parts of this. And you can actually put this together. This is a company we spun out last year. We sold it for actually $20 million, right, off the block. That basically takes this sort of information, generates a behavior pattern, and uses that to design an offer that you can give people. All right? This is why you don't own a mobile phone. And on the basis of that offer, they feed it to the customer, and they feed back, did the customer respond? And you update your model every hour. All right? So this is the kind of models that are now going on. You're building really quite deep behavioral models of people, all right, in order to understand how best to use them, manipulate them. This sounds awful, all right? But this is the kind of thing that's actually going on in the industry for one reason or the other. You can use it in lots of different ways. This is another spin-out company we generated called Incoming Media. And again, what it does is it actually, it's a company that basically, the problem with mobile phones is about 60% of bandwidth is taken up with video these days, 60, even 70%. So what you'd like to be able to do is to preload, while you're in Wi-Fi range, all the things that you might want to watch in the future. So what I'm going to do is I'm going to put a piece of data analysis code on your phone, and I'm going to see what you watch, and I'm going to use that to predict what you will be watching in the future. And even better than that, I'm going to talk to all your friends on social media and find out what they've been watching. All right, and I'm going to use that to predict what you're going to watch, okay? Again, this company just raised $6 million, okay? And you can kind of see why, again, I don't use a mobile phone. Here is something that I do like, and this is my response to not owning a phone. I think this is the way this kind of data analytics is going in the future. It's going to be such that we really worry, I don't know about you, I worry about privacy a lot. But there are ways now of actually really constraining it and really doing personalized analytics. And I'm actually going to focus on this application over here. This is a health application. This is work we've recently completed for Barclays in London. And what it really does is it allows you to vertically integrate all your information on your own personal device. So your bank data, but you'll notice here also your Vodafone data, or your bank other information, everything you do in a personal data vault. Okay? And that personal data vault is then encrypted. All right? So you actually ensure that no one, not even the bank, can read it. But what you can do is you can send analytics to the data now. All right? And you send analytics, and these days there are these techniques called homeomorphic encryption that allow you to actually run data and machine learning algorithms on encrypted data without unencrypting them. All right? So the modern future for this thing is people will own their data. That's what really should happen in this case. And banks and Google and everyone else should actually send their analytics to people. And people should choose to accept that information or otherwise. All right? That's really the definitive model for these. Over here, this is actually a health example. I had my genome sequenced last year, and I have it, because I don't have a phone, I have it on an iPad, okay? And I have it encrypted, and I have my phenotype data on that device as well. And now, if my doctor comes along and says, what kind of dose do I need? They, in principle, can send analytics to me, look at the encrypted data and actually compute, all right, what dose they should give me based on that information without ever seeing the information. All right? So there's a future out there that I think, in my view, is personalized analytics. And it has the added advantage of potentially destroying Google, which I kind of like. So one last thing I want to talk about is infrastructure. In Australia, this is a very big issue, the amount of investment that goes on here. And analytics is a really interesting kind of thing to apply. And we've made a number of interesting investments in this area. And I'm going to talk at least about one of them. Typically, the kinds of problems that analytics work well in are problems for which you don't actually have a good mathematical model. All right? So, you have a good mathematical model perhaps for how a wing works, but you don't have a good mathematical model for how a road fails. So how do you predict, what kind of model can you build? And of course, the right model is to use data to build the model directly. And I think this, again, opens up a whole new vista of opportunities in this space. And we've done a number of projects, but I'm going to talk about one that I think is particularly compelling. This is one that we've been working on for about a couple of years. We've just spun out a company in the area, and it is designed to predict the failure of high-pressure water mains. Okay, so at the moment there are all these fluids guys out there. Sorry, Alistair, I can see you there. In which basically people build Buckingham Pi theorems and try and predict what's going to happen in a water pipe. But the problem is, it depends on so many other factors. It depends on the amount of road traffic over the top of it, the soil acidity, the weather conditions in the last 70 years, all these things. And you want to be able to put all that information together in a way that you can actually use to predict what's going on. So we designed a system, and I'm going to talk about it in a minute, that basically puts information not just from the company itself that says this is the type, this is the age of the material, but what's the soil acidity? What's the traffic flow in the last couple of years over the top of it using traffic light information? What's the rainfall been in the area? All these sort of things, and puts all of them together in a data-driven model. That is, you don't actually build a mathematical model, you literally map the data directly to the failures that have occurred in the water system, the so-called non-parametric model. I think these are really going to come together. And then on the basis of these non-parametric models, you then make a prediction as to which impacts that different types of things, and then which water mains are going to fail. So this is a map of Sydney of all the high pressure water mains. And here what you're actually seeing is green is a low probability of failure, blue is higher, red is high. And if I've got a fixed maintenance budget, this is where I should spend it in the next 6 months. Okay? So in this case, when you look at what happens with the standard failure models like Weibull and things like that, this represents in Sydney alone about a $200 million saving in maintenance costs, because you can actually predict much more accurately using much more information the types of failures that are going on or could happen. So we've applied it now in places like London, all right, which is a very interesting place because they have very different types of mains water, and also in a number of other different types of cities. So there's an interesting kind of thing here. And now applying it also to different types of infrastructure like gas mains, all these sorts of things. So data analytics, I think, has a real role to play in really building and managing large-scale infrastructure. And just one last example here. This is, again, the same sort of thing where we're actually using analytics in this case to predict the impact of building new infrastructure. So now you ought to be able to use this to actually design the future, what's going on here. So coming all the way back to the beginning, this is Port Botany, okay? This is all the data that actually exists about the whole supply chain, not just from the port, but all through the rail network, right out all to the intermodal yards and things like that. Lots of different sets of data in here about the loading, the unloading, the effect of trains waiting up here, lots of different things like that. But you can build from this good models, probabilistic models of what different types of trains in different types of forms will produce what kind of throughput and this sort of thing. And actually on the basis of that, choose the different types of infrastructure that you want to invest. So we actually managed successfully to stop the government spending $200 million doubling up the rail up here, all right? Mainly because we showed that all these trucks that are queuing, all these trains that are queuing up here are not queuing up here because there's a lack of resource, because actually the data shows that there are too many trains stacked down the bottom here, all right? So you can build now some quite sophisticated models that actually predict what different types of infrastructure will perform. So there are enormous opportunities. I think there's a whole wealth of stuff that's come out of the robotics background and out of these sorts of techniques that can really be applied in lots of different domains. And I think we really need, as engineers, to open up our minds to how to do this. Now, the last slide I really wanted to bring up, and I don't know whether Michael Osborne's in the audience. Good, Mike, so you'll recognise this. This is work that Frey and Osborne did that we've sort of repeated for Australia. And what it says is, you know, in the next decade or so, how many people are going to be displaced by the sorts of technologies that I've shown you? And it's not just robotics, it's the fact that there are lots of jobs that AI is going to replace or supplement in some kind of way. And I think there is some interesting numbers in here, and I will say take all of this with a spadeful of salt, okay? Because, you know, your ability to predict the future is not good, but it does tell you something about the present, all right, and what we perhaps should be doing in the present. The first thing to show is that in Australia, we estimate about 40% of jobs will go within the next 10, 15 years. That doesn't mean there won't be new jobs, all right? And I think we all need to look to what those new jobs might actually be. And also as universities, we need to think, what kinds of people are we training? Because a lot of jobs that are out there now really are disappearing. But the more worrying ones are this one here that show that there is actually a polarization in jobs that's occurring because of automation. So we're going to see a lot of people who are in clerical roles or in labouring roles and that sort of thing who are not going to get jobs in the future. And people who are professionals are going to keep their jobs. And so increasingly what automation, what AI is doing is not changing employment from the bottom, which is what's happened in previous industrial revolutions, it's hollowing out the middle. All right? And you see that very directly in the kinds of characteristics of jobs that are out there. Now, we've done one extra piece of work beyond what Mike Osborne's been doing, which is to actually map that spatially across Australia to try and get a sense as to what's going on in the country. And again, a spadeful of salt here is essential. But nevertheless, you are seeing obvious trends, which I think people are anecdotally sort of coming up with. The first one you'll notice is that the big unemployment levels are in the mining areas. In remote regions are basically going to become even more depopulated in Australia because there's no reason for people to be out there anymore because we've just automated the whole lot. Okay? So all the good things I've been showing you in some sense have a downside as to what's going on. And I think this is important information for the way government's behaving at the moment. I think the second thing is this thing that's going on around the whole urban communities with the new, Silicon Valley mantra. Where you've got density of professionals, you get more jobs. All right? This is a map of Sydney, and what it shows you is the CBD and the coast where everyone wants to live, who's got a good job, who's got a PhD, who's doing sort of startups. That's going to be great. But you go out into the suburbs and everyone's leaving. All right? So again, I think there's this polarization geographically that's happening that I think is a little bit of a concern. So let me leave, and basically I couldn't actually go this talk without getting this video, okay? In the following sense, that I've really, the stuff that we've been doing in robotics, the stuff that's going on in machine learning, I think there are just enormous opportunities out there for the whole engineering community. But at the same time, I think we need to be a little concerned about what it is we're doing. And that last overhead that I showed you there said, maybe we need to be rethinking the way that we actually teach in the future, not just in engineering, but right across the university spectrum. I mentioned one thing, we're trying to push at the moment for what we talk of as a freshman data science course. Everybody, even an arts degree person, should be doing a first-year course in data science, because even if they're not technology practitioners, they will be technology users in the future, and they will be, their field will be disrupted and transformed, and we all need to be concerned about that. So, yep, I think the future is no longer just science fiction. I think I've showed you here, we now have gone from the point of having robots in the lab to robots that really make money out there, and I think that's been an interesting transformation. I think we are seeing the same thing in AI in lots of different spaces, but I think there are great opportunities for not just Australia, but also the UK. So, thank you.
Well, I'm sure you'll agree with me that was a truly amazing lecture. It's covered just about every branch of engineering that we have in our department, from information engineering to civil engineering to fluid mechanics, and even went into the social sciences towards the end here, Hugh. So that was absolutely fantastic. The tour d'horizon was just complete. Can't think of any part of engineering and its impact on the world that was sort of missing there. We do have time for some questions. I'm sure there are multiple questions. We have about 5-10 minutes for questions. Who would like to go first? So I'm now going to call upon Lyle Lubbock, who's the grandson of Maurice Lubbock, to propose a vote of thanks to Hugh Durrant-Whyte.
Well, I think, I hope most of you will agree that we've heard something rather special today. The sheer range and breadth and scope of what we've heard through all the applications that we've seen described is truly breathtaking. Just to illustrate, my son is working in human genomics and very much using machine learning to drive his work. My brother is working in sort of pipelines in New Zealand, so throughout just my immediate family, I've immediately sort of latched on to the applications that have been described here, and I'm very much going to be on the phone to both of them talking about what I've heard today, and perhaps suggesting they look at some of your work. Certainly the range of applications for me was dizzying. It's really hard to see almost where you can't apply this. I expected something from the numbers, which are very pleasing, that have come along today. And I must say, you lived up to the reputation and hype that have been given to me, partly by the people coming and partly by the preparation that I've had with people sending out papers. The other thing that's very pleasing to me is that Maurice Lubbock, his whole ethos in life was, don't just be an engineer, you've got to learn how to use that engineering in the world out there, how to apply it, how to manage it, and I think what you've had to say today, particularly in the sort of sphere of using your data, and for me the most exciting thing is how quickly you can sort of get back to real-time views that come out of this data and how important that is to actually running and managing things, he would have been really excited by that. And so I feel a very strong family connection to what you've said. So I like the other way that after having described some of what you did and the work that you've been through and certainly the history of how you got there, you weren't just interested in sort of getting what you can out of it, but you were interested in the impact on society. And for me, I suddenly had a whole level of extra interest where you started talking about the resistance that some humans are going to have to some of this technology, and the idea that not owning a mobile phone, for example.
I hope I've scared you.
You have scared me. But like you, I'm a great advocate for privacy where it's important. And I think this idea of humans taking control of their own data and then allowing permissions to use that, I think is a very important point that's come out of today. And I hope it's a direction that you and all your colleagues and people that work in this field encourage, because with those kind of safeguards, I think we have far less to fear than some of the apocalyptic pictures that have been painted. I've seen about Stephen Hawking, for example, putting out a scare about what he thinks is going to happen. So, I think the more that people like you look at the impact of what they're doing and consider that, and particularly with this hollowing out of the middle that you talked about, society has got to come to terms with that and work out a way of dealing with that. And okay, the solutions aren't there yet, but I think at least we've identified the problem, and we must get on to what the solutions are going to be so that we don't get these huge inequities in society. Anyway, I would like to thank you and everyone else involved in today. I think the Australian theme has worked marvellously. I like the earlier lectures, and I think without exception the speakers throughout today have been very engaging and certainly kept my attention rapt throughout. So I'd like you all to join me in thanking our speaker for today and give him another round of applause.